So up until now, we've really just been discussing, besides the chow test, we've been really talking about what happens with these binary variables when they're independent variables. Now let's start talking about what happens when we have a binary or dummy variable as our dependent variable. And this is going to lead us to discussion of the linear probability model. Let's spell that a little bit better. Probability model. So in this case, now the dependent variable, so the y variable, is 0 or 1. So we have this y equals beta 0 plus beta 1, x1 plus blah, 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 plus beta k, xk plus u. And this now is a 0, 1 variable. And so the key thing here is that we cannot interpret the beta j, so one of these slope parameters, or any of the betas really, the same way as before. I mean, y either, sorry about that, either changes from 0 to 1. So if you change one of the x's, y is changing from 0 to 1 or not at all. So we just have to change our interpretation just a bit. So let's explore that. So the expectation of y given x, the expectation of u given x equals 0, that's one of the assumptions we make, right? So this is what our expectation of y given x is equal to. Essentially, this u is being dropped off. And how to think about this is the probability that y equals 1 given x. So the probability that y equals 1 given x, that's what this is capturing. So this is the probability that y equals 1, or the probability, sometimes you'd say, of like success in terms of y being equal to 1. So that's what this is capturing, the probability that y equals 1, which is going to help us with think about our interpretation. So let's erase this and think about the interpretation. We can think of a couple issues with these linear probability models as well. So we just saw that the expectation of y given x, which was equal to these beta zeros plus beta 1, x1 plus all the way up to beta k, xk, we could think of that as the probability that y equals 1 given x, right? So it's the probability that y actually equals 1 given these different values of x, so x1 up to all these x's. So the probability that y equals 1, we're making this assumption that's a linear function of x, or of the x's, right, of all of our independent variables. So that means the change in the probability that y equals 1 given x equals the probability, or sorry, the beta j times the change in. I don't know why I put change twice, but beta j times the change in xj. Ooh, that was hard to say for some reason. So the probability that y equals 1 is a linear function of these x's, right? And so that means the change in probability that y equals 1 given x, if we hold all the other variables constant and these assumptions hold, is beta j times the change in xj. So now these beta j's measures the change in probability of y equals 1. So it's the change in probability of y being equal to 1 when xj changes. So it's about this change in probability of seeing of y being equal to 1. So for instance, if we estimated this regression or a regression, there's the hats because we've estimated it, and it can't be a U because there's the hats on it. What beta hat 0 is going to be measuring is the predicted, so it's predicted because it's estimated, probability that y equals 1 if all the x's equals 0. And then the beta hat 1 here is measuring the change in probability, so the change in probability that y equals 1 from this change in x1, holding x2 and all these other x's constant. So it's about the change in probability of saying y equals 1. That's how we're thinking about these changes in the slope variables. The intercept, just like you'd imagine it's capturing the probability, the predicted probability that this dependent variable equals 1 when all these x's equal 0.